Swayam Prabha. Digital India. Educated India.
Welcome back to the course on Symmetry, Stereochemistry and Application. In the previous lecture, we were discussing about isomerism and we started with talking about various different types of isomers and we were trying to understand what are chiral compounds. So in this course, now we need to learn a new method of projecting these chiral molecules, which we all know as Fisher's projection. So how do we represent a molecule, a three-dimensional compound, on a two-dimensional plane, that is on a blackboard or a piece of paper? We have already learned how to draw the wedge and dash projection. We have also learned the Newman projection and the cyclohexane chair form, boat form, how to draw those and all that. So now in this lecture, we will try to understand how to draw a Fisher's projection. So we'll concentrate in our discussion on molecular representation by Fisher's formula, mainly in the next part of this course. So the first question is how the Fisher's formula is drawn. We draw two types of lines, one vertical line and one or more horizontal lines depending upon the number of stereocenters in the molecule. The point of intersection of these lines is considered as the stereocenter. This formula can be drawn only for molecules with stereocenter. That is very important. We should not draw a Fisher projection for a molecule where there is no stereocenter present in the molecule. So how does it work? So in case of a Fisher projection, we first need to identify the different groups that are present in the molecule. We need to identify them with the numbering. So most prior groups like carboxylic acid, aldehyde or cyanide kind of functional groups should be placed at the top and given a number 1. And then from that, the chain should be drawn from top to bottom. So now the way this molecule is shown, I have a model here. Suppose this group is one OH group, the red one, and that is my most important functional group. This red is here. So the way you see the molecule is that at that particular carbon atom, on the top first carbon atom, you have two red groups pointing towards me, and on that group you have two atoms pointing like this, two atoms pointing like that towards you. And this is how it is shown in this first figure on the left hand side. The groups 1 and 4 here in my case are those two red atoms which are pointing towards me, and these two groups and those two groups are pointing towards you. So now the way this projection is drawn is that the CC bond which is in between, the CC bond is drawn on the plane of the board, and based on that CC bond, the two oxygens which are below the plane of the board are shown as dashed lines, and the two other atoms which are on the right and left are shown as the bold wedges, which are indicating that these two are above the plane of this CC bond. So when you draw this molecule like that, you simply convert it into a diagram like this. So when we have the vertical line, the terminal atoms on the vertical line are below the plane of projection, and the atoms on the horizontal line or the side atoms on the horizontal line are above the plane of projection. So this orientation of drawing has to be kept in mind whenever we draw a Fisher projection. So the way we see such a molecule is to see the molecule like this. We should see from one particular side and try to draw the molecule as we see the molecule. So from your side, if you see the molecule like this, what we see is from your side is that the hydrogen is on top, oxygen is bottom. So we should rotate it like that so that the oxygen is up and hydrogen is down. So what we do is oxygen up, carbon and hydrogen is down. Maybe this is OH and that is hydrogen. And these two groups can be a methyl group and it can be a chlorine atom. Now the way we should draw this is slightly different. What we should draw is to convert this into a Fisher projection. It would look like that. So this is how we should try to draw the molecule. So here in this figure, the observer is seeing the molecule in such a way that A and B are below the plane of projection, C and D are above the plane of projection, and that is how we thought about it, and then we have drawn the molecule like that. So here in case of a few real molecules where we have drawn the molecule like this, we have methyl groups, we have bromo, OH, hydrogen and hydrogen, and it is obvious that the connectivities of this carbon and connectivity of those carbon and the groups are different. So those are chiral centers. Both of them are chiral centers. So now if you rotate this molecule in such a way about this bond that the two hydrogens are on one side and the methyl groups are below the plane of the board, both the methyl groups, we see this molecule like that. We have rotated the entire molecule about that CC bond. So now by rotating, we see that this methyl is below the plane, that methyl is below the plane. So those two groups have fallen in the vertical line, and the hydrogens which are on the right is here in the horizontal line. The bromine and OH which are on the left side are also on the horizontal line, indicating that those four atoms are pointed upwards from the plane of projection. So now if we draw the mirror image of this particular molecule, we can draw it like that. And when we go back to the other side, try to understand that what happens if you draw it in this way with the wedge and dash formula, we end up getting a different molecule. So these two mirror images are not superimposable on one another, and therefore these two are two different enantiomers. Similarly, here what we see is that this molecule we rotate in such a way that just rotate the top carbon to put the methyl group to the back, we get this condition. And then when you draw the Fisher projection, the two methyl groups on top and bottom are below the plane of projection. The O and H here and that hydrogen and bromine are pointing upwards from the plane of projection. Similarly, the corresponding mirror image would look like this, and that mirror image corresponds to this molecule because this methyl and that methyl are below the plane. And then again, you just rotate the molecule about its top CC bond axis. You will get this molecule which is different from that starting point. So these two compounds are again non-superimposable mirror image relations. So now when we talk about glucose, you see that this molecule has 4 chiral centers which are marked as stars. So the way we try to draw this in a Fisher projection is shown here, and there are 2 different combinations of glucose which are D and L, and what we see is that these 2 are basically mirror image of one another. This OH and OH are mirror, hydrogen and hydrogen are mirror, and OH and OH are mirror. So when you invert every chiral center, the chirality of every center, you get the other version. So when we see that the 4 atoms that are connected to one center gives rise to 2 different isomers or 2 different compounds, then we must identify those isomers using some nomenclature. So the stereoisomerism resulting from single center of chirality, we have to have a stereochemical designation. So when we try to designate again, if you remember our rules of IUPAC nomenclature, we had to prioritize groups, and based on the group's priority, we had to give them numbers, and then based on those numbers, we used to identify a molecule and write the IUPAC name of a compound. So in this case, we need to prioritize those groups which are bonded to the carbon center and put them in a given priority order, and then the chiral center is observed viewing with A, B and C, which are high prior groups pointing towards the observer, and the lowest prior group D pointing away from the observer. So what does it mean? It means that suppose if I have this molecule and I need to prioritize these groups, maybe this is A, that is B and that is C, and we should look at the molecule like this. The hydrogen has the lowest priority, so you should look from the direction opposite to that particular hydrogen atom and look at the molecule and try to identify whether 1 to 2 to 3 it is clockwise or 1 to 2 to 3 is anti-clockwise, and based on that we will identify those centers as R and S. So when you see that when the path A to B to C makes a counterclockwise course, that is called S. So in this particular case, it is the opposite. In this particular case, if I say that the red is 1, blue is 2 and this violet is 3, 1 to 2 to 3 is anti-clockwise. So this particular compound should be termed as the S isomer or syn star isomer in Latin, which means left. So 1 to 2 to 3 here is anti-clockwise direction. Remember that you are viewing from the direction opposite to the 4th group. If I take the second molecule in the same orientation, what you can see is that 1 to 2 to 3 is now clockwise rotation. 1 to 2 to 3 being in clockwise rotation, we call it as rectus in Latin, which essentially means right. So clockwise rotation from priority 1 to 2 to 3 makes it R, and anti-clockwise rotation makes this nomenclature as S. So we identify stereoisomers by writing R or S with the chiral center. So when we have multiple chiral centers, we would follow the rule to identify those chiral centers in terms of their priority, and then we apply various subrules. So the first rule is first sequence rule. Atoms are arranged in an order of preference that decreases with decreasing atomic number. So if you have different groups connected to a central atom, then the group with highest atomic number gets priority over the atoms which are having lower atomic number. So in this, the order is iodine, bromine, chlorine, sulfur, phosphorus, fluorine, oxygen, nitrogen, carbon, hydrogen, like that, which are in general present in various organic molecules. A free electron pair is considered as phantom atom with atomic number as 0 and is given the lowest priority. So now use a first sequence rule, 1 bromo, 1 chloro, ethane, bromo, chloro, carbon and hydrogen. And then we draw the molecule like this. You have two different isomers that are drawn here. Now we see the molecule in such a way that the hydrogen is on this carbon is behind the hydrogen carbon, and on this it is behind this carbon. And then we try to see the priority of those groups. So bromine gets number 1, chlorine is number 2, and this carbon gets number 3. So 1, 2, 2, 2, 3 is a clockwise rotation, so we write it as R. And in the other case, the bromine 1, chlorine is 2, and that methyl group is 3. So 1, 2, 2, 2, 3 is a rotation in anti-clockwise direction. So this is the S isomer of 1 bromo, 1 chloro, ethane. Now, in most of the cases, we see compounds which has multiple stereocenters or multiple chiral centers. So, in those cases, we have to have a priority on those chiral centers as well. Acyclic molecules with n number of non-identical stereocenters of chirality gives 2 to the power n stereoisomers, which are enantiomeric in pairs. We will discuss about this in a few minutes. It applies to only molecules with non-identical chiral centers, so called the unsymmetric molecules. Consequently, the symmetric molecules have fewer than 2 to the power n stereoisomers. Let us see with one example. So we have, in this case, two non-identical centers of chirality. So what we have here are the chiral centers at this and these points. And these two chiral centers are not identical in the sense that the substituents are different in these two centers. So therefore, it should have 2 to the power 2, that means 4 isomers, and those 4 isomers should be enantiomeric pairs. So the way, first we can draw this molecule as shown here as number 1. And the corresponding mirror image is drawn here as number 2. So this 1 and 2 are mirror images of one another, so a pair of enantiomer. And now if we look at the lower molecule in blue, They are called diastereomers because their case they are not mirror image of one another. What we see here is that if you place this particular molecule next to this molecule 3, the difference is there only in one chiral center, which is this one. The other chiral center has the same chirality. Similarly here, the difference arises in this chiral center and not on the other one. So these molecules are called diastereomers. Now if we have a different molecule where we have two identical centers of chirality, when we say identical centers of chirality, it means that the groups associated with each of those chiral centers are same. So what we have here is that carboxylic acid, OH and hydrogen associated with this carbon center, and here this has carboxylic acid, hydrogen and OH associated with the second chiral center. So both the chiral centers have same set of groups. So we say that two identical centers of chirality, and what we have is here is RR and SS, because these are the two centers designated as RR and SS. Whereas the other possibility, we are keeping this group here same, we change the second one and make it this one. The corresponding mirror image of RS becomes SR. But what we see here is that there is a mirror plane in these two molecules. So these two molecules are not different. They are the same molecule because you can rotate this molecule about 180 degree in plane like that and superimpose on the other molecule. So they give rise to the same molecule. So this particular pair of isomer is called the mesocompounds, and it forbids the chirality of this molecule. So here, instead of having 2 to the power n, we have 2 to the power n minus 1, that is 3 different isomers, where these two are enantiomers and here the relationship is a diastereomer. Where diastereomers means they are not mirror image of one another. So when we talk about diastereomers, we should know what is the difference between the diastereomeric pairs. Diastereomers have different chemical and physical properties in any type of environment. So when we talk about S-tartaric acid and the mesotartaric acid, the optical rotation about which we will discuss in the next lecture, the compound SS has a specific rotation, which means it is chiral, whereas the mesotartaric acid does not have any optical rotation or specific rotation, therefore it is achiral. They have differ in melting point a lot, their densities are different, and their solubility in water in grams per liter is also different, and these differences are because of there being two different set of compounds and two being diastereomers of the same compound. So in the next lecture we will discuss about the optical activity and plane of polarized light and how the optical activity is used to identify various chiral compounds. So in the next lecture we will start from here. Thank you.